Good day, everybody. Today, what I want to look at is finding the probability of each of the planets, Mercury, Venus, and Mars. What percent of the time is each one of those planets closest to the Earth? So I've got some analysis here where it was done numerically, but I want to do it analytically. So the first thing is that this paper was showing that most of the time Mercury is the closest, and on average Mercury is the closest, even though at its closest point Venus can get closer to the Earth than any of the other planets, but it can also get a lot farther, compared to Mercury. Quick little run through. There's the orbits. So you've got Earth in blue, and you can see Mercury's close, then far, but it doesn't get as far as Venus, and so on average it's going to be closer. So let's investigate this analysis. First, let's look at a diagram. So here's a picture of our situation. We're going to assume circular orbits for the planets, and that's a simplification that'll make the math easier, and I don't think it matters too much because if you think of the elliptical orbit going over and over for both planets, sometimes we'd be farther, sometimes closer. Hopefully in the end it kind of evens out, as time span goes to millions of years or something. Anyway, using circular orbits, you can put an axis, we'll assume the planets are in the same plane, then Mercury can be at any angle, Earth can be at any angle. From the law of cosines, this distance is a squared plus b squared minus 2ab cosine of that angle. And so that angle will be just given by, say, s minus t. Here I drew it so s minus t kind of gives this angle, but the cosine of this angle is the same as cosine of 2 pi or 360 minus that angle. So the angle between the two, the cosine of that is the same as the cosine of this angle. So it doesn't matter which of the two angles you use. So this will work regardless of how s and t are set up. So there's the distance thanks to the law of cosines, with Earth being 1 unit away from the Sun and Mercury being, say, 0.387 astronomical units away. And it won't be surprising that in a way we can think of maybe the Earth fixed and then just let Mercury go around its orbit. So in a way it's kind of, what's the relative angle if you move the x-axis so that it's always in this Earth-Sun line? Then out of all possible angles the Earth and Mercury can make, it's the same as just Mercury being from 0 to 360, 0 to 2 pi, with the Earth fixed there. So here would be the average value, 1 plus a squared minus 2ab. So I'm using b as 1, the Earth's distance. And if I want the average value out of all possible angles for both s and t, 0 to 2 pi, 0 to 2 pi, so if I divide by that measure, it'd be 4 pi squared, then this is the average distance. Or as we fix the Earth and just let Mercury's angle go 0 to 2 pi, of course we get the same result. And notice there's symmetry. So I could go negative pi to pi or just 0 to pi. So if I do the integral from 0 to pi, I'm obviously going to get the same thing and divide now just by the pi. Right, so as Mercury's angle, s, goes from 0 to pi, if I find that the average distance that way, and then if I continue it from pi to 2 pi by symmetry, we would have the same average if we just do 0 to pi or 0 to 2 pi, or negative pi to pi. I sometimes doing some figures. And so with the other planets, similar. There's with the S and T, and divide by 4 pi squared, the measure of the total amount of angles for S and T, or just going 0 to pi for the angle T I used for Venus. So Venus on average is going to be farther away, 1.13, whereas Mercury on average is about 1.3, 1.04 units away. Right? So over the course of millions of years, if you calculated every day how far Mercury was and then average that, versus if every day you calculated how far away Venus was and average that, Mercury would be closer. And Mars will be farther. So 2 ways to do the average. So again, there's the results that we got for Mercury right here. And as mentioned in the paper, the average distance for any two planets can be found in terms of an elliptic integral. So I'm fixing one of the planets to be the Earth. Well, all right, so I'll put it this way. So this law of cosines distance, if I just go 0 to pi, can be put in terms of the elliptic integral. And then these are the values we got for Mercury, Venus, and Mars, their average distance to the Earth. Just to mention the elliptic integral kind of quickly, here's the incomplete elliptic integral, where the upper limit, you have a variable theta. Ours involves the complete elliptic integral of the second kind, so the upper limit is pi over 2, and for the math I need, for the complete, if you go 0 to pi over 2, it doesn't matter if you have sine squared or cosine squared. Right, so these will be the same. You can, if you know the graphs, it should make sense to you, but we can prove it with a substitution as well. You just let u equal pi over 2 minus theta. You can solve for theta and du, and so then the new integral, theta went from 0 to pi over 2, so u will go from pi over 2 to 0. Because of that, I've got this negative du, put the negative there, and now I have sine of theta, which is pi over 2 minus u, but sine of pi over 2 minus u is the same as cosine of u. So, of course, it's the same. And if I want to show this law of cosines formula, gives me the elliptic integral. A little quick math here. First, do a substitution. Theta is over 2. So then I get 2 d theta is ds. Bring that 2 out. Change that to 2 theta. And then double angle formula. Cosine of 2 theta is 2 cosine squared theta minus 1. Distribute. Factor out a plus b squared. If you pull it out front, because you factored it, then it looks like this. And by what I showed above, if you do the full complete integral, go 0 to pi over 2, it doesn't matter if you have cosine squared or sine squared, you get the same result. So I'll just change it there. And then, so this is my k squared, so it's that, as mentioned in his paper and what I have right there. But it's just as easy for me to just do the definite integral on software. So for the pairwise comparisons, we've got Earth, Mercury, Venus, and Mars. Only those planets can be closest to the Earth. Jupiter can never be the closest. It's too far away. Mercury will always be closer than Jupiter is. So it has to be one of these three as at any one point the closest planet. So I'm going to compare them in pairs. Compare in pairs. And the way we do that, well, we do the law of cosines for each of the two planets. Like my A will be 1 if I fix Earth. And then, you know, if I want to compare two other planets, like B1 could be Mercury and B2 could be Venus or something like that. But so I want to solve for when they're exactly equal. So I put the equations equal to each other. I don't think it was important, but I made it so that I had a positive cosine term. So I switched sides here. A squareds cancel, and then you can subtract the b1 squared, divide by 2ab2, and then do arc cosine, and that'll be theta 2. Now cosine's even, so there's really a plus or minus here, because if you have a negative, cosine will be absorbed. And so it's better to kind of think of theta going from negative pi to pi rather than 0 to 2 pi, theta 1, theta 2. And I also solve for theta 1. I mean, it's symmetric, but sometimes it's better to solve for one angle compared to the other, as we'll see in our plots. So here's the same work, but done with numbers. And I solve for the angle T, which is Venus. Let's not forget that. Probably should have had S Venus, but I have R for Mars. That's good. But T for Venus and S for Mercury. That'll stay consistent throughout. All right, so we solve for the angle T, which is Venus's angle, as a function of angle S, which is Mars's angle. Here's the equation. Put it with fractions as well. It's prettier. Let's look here. If I look at, there's Earth. If I draw circles until it first touches Mercury's orbit, when it does so, Venus's angle right here is at 0.65 roughly. I think I solved it with more decimals, but I mean, so roughly it's 0.65. So if the angle from Earth, well, if the angle Mercury makes with the x-axis that contains the Sun and Earth, if Mercury's angle is 0 and Venus's angle is 0.65, they'll be the same distance. For any angle less than 0.65, there's no angle for Mercury. Venus will definitely be closer. So as I keep expanding this distance, if the angle Mercury makes is pi, it's right here, and that's this angle, the angle with Venus, so it's right here, is about 1.85. So it's more than pi over 2, as you can see. But now they're the same. And so if Venus has an angle bigger than 1.85, we're guaranteed Mercury's closer. So you can see that. If Venus's angle is more than 1.85, Mercury will be closer, and this is where they're equal. I threw in one more here at pi over 2. That's for the angle of Mercury. Venus would have to have an angle of 1.31, less than pi over 2, to have the same distance. So here's a plot, and everywhere above this plot, Mercury is closer. And also below here. So in between here is when Venus is closer. Okay. So if Venus's angle is below 0.65 or negative 0.65, we're going negative pi to pi. Venus is definitely closer. Then here's where they meet along these two curves. And then we can just find the area under this curve, and that'll be the probability that Venus is closer if I divide by the area of this square, which is pi times pi, so pi squared. So this fraction of the area is the integral under that curve divided by pi squared. That ended up being about 0.409. So Venus is closer almost 41% of the time. Of course, that means Mercury is closer about 59% of the time. if I want to compare Mercury with Mars, I put those two distances equal to each other, then solve for the angle R. It's this arc cosine with the plus or minus. There's our curve. So again, Earth actually is closer to Mars if both angles were at 0. So if I draw this circle where it first touches Mercury, then the angle for Mercury will be 0. Right? We're kind of using these angles again. Earth's fixed, and the angles, we'll use negative pi to pi, although I'll focus on 0 to pi, but just use symmetry. So now, again, if Mercury has angle 0, Mars would need angle 0.26 in radians, of course, to have the same. And that's decimal approximation, but so roughly 0.26. If the angle for Mars is smaller, then it's definitely closer. There's nothing Mercury can do. And then if Mercury has angle pi, again, S is the angle for Mercury. It's 1.09 is the angle for Mars. So if we look at that, it's almost 1.1 radians. It's more than pi over 3, but less than pi over 2. And I also graphed if the angle for Mercury was pi over 2, for Mars it would have to be right there, 0.78. Well, it's almost pi over 4. So almost a 45-degree angle when that's 90-degree angle. That's interesting. Anyway, so Mercury is closer above the curve. Mars is closer in between the two curves. Again, if you just focus on the first quadrant, so this area under the curve tells me the percent of time Mars will be closer. If I do the area under the curve divided by the area of the pi by pi square, so that comes out to be about 23.3% of the time Mars is closer, and the rest of the time Mars is farther away, 76.7%. Again, there's a lot of angles. Once the angle is more than the 1.09, Mercury's closer no matter what for all those angles of Mars. All right, so lastly, if we look at Venus versus Mars, now we first reach Mars when Mars is at 0 degrees. Venus will be at 0.59 degrees. So that's right here. And then as Venus goes to pi degrees, for a tie, Mars would be at 1.45 radians. Did I say pi degrees? Pi radians. If Venus is at pi radians, for a tie, Mars would have to be at roughly 1.45 radians. And so, of course, if Mars has a bigger angle than that, Venus is definitely closer. So Venus is going to be closer outside that curve. So here it is with more decimal places. Mars will be closer in between the curve, right here. So I want to integrate below the curve, but from this intercept to pi, and then divide by the length of the area of the square, the pi by pi square. So about 26% of the time, and then almost 74% of the time, Venus will be closer than Mars. Now, if I take those three curves and extend them into 3 space, so depending on which projection I'm looking at, like this could be Mars and Venus right here, and then just extend it with Mercury being any angle, and so on. We can take this curve, I can't remember if that was Venus and Mercury or whatever. We've got another one, Mars and Mercury. So I just extend those curves into 3 spaces, moving it perpendicular in the other axis direction, then I get this nice looking picture. And in each of these regions, well, these surfaces represent where there's a tie between two of them. There is a lot of symmetry. Again, there's 8 octants and they're all symmetric. So here we are in just the first octant. Notice they intersect along a curve because what they represent. Like, so this one surface, I forget which one's which, but one surface represents where Mars and Venus are equal, and then another surface might represent where Venus and Mercury are equal. And well, if those two surfaces intersect, two surfaces will intersect in a curve, but it'll be the same curve because, well, if Mars and Venus are equal and Venus and Mercury are equal, well, now Mercury and Mars are equal. So, two surfaces will intersect in a curve, but because of this way we've done it, actually all 3 will intersect in a curve. And now there's 6 regions in this 3 space, depending on the order, the 3 factorial ways to order who's closest. So we can reason it out. I also used a nice little function that's either 1 or -1, depending on the sign of your argument. And so here's this function I made that'll tell me the order of who's closest. For this function, I'm going to plug in an angle that gives me Mercury's angle, Venus's angle, and Mars's angle. And then I can determine who's closer, Mercury or Venus. And then this will either be positive or negative, or I guess it could be 0. But then if it's positive or negative, it'll give me 1 or -1. And same with this. This is Mercury and Mars. And it'll either be positive or negative. But now I multiply by 3. And then this is Venus and Mars, but now I multiply by 9. So this will either be 1 or -1, then times 9. So the biggest value I can get is 9 plus 3 plus 1 is 13. The smallest I can get would be the negative of 13, and so on. So just depending on, here's what can happen out of all the outputs from that, from this function of the 3 angles. I included ties, so if you're on the surface, right, so like if this were 0, so if these two were equal, then this would be a 0, and then so I would add 1 plus 3 perhaps, and so I could get a 4, where if Venus and Mars were equal, or a -4. Right, so I can determine by the output of the function. So like if I plug in the angle 1 radian, 2 radians, 2 radians for Mercury, Venus, and Mars, then I can see who's closer. All right, so we got -13. So here I am in this region. -13 tells me Mercury is the closest. Now, where else Mercury is the closest? So at 1, 2, 1, this function outputs to 5, which means Mercury's closest. So in either of these 2 regions, Mercury's the closest. This separates Venus and Mars. So who is closer between those 2? Up here, Venus was closer than Mars. And in here, Mars is closer, but I mean that doesn't matter between those 2 because Mercury is closer than both of them. So that was just between second place. So in these 2 regions, Mercury is the closest. Sub in 0.7 for Venus's angle and 1 for, or 2 for Mars's angle. Then I'm over here. We get -11. That means Venus is the closest of the 3. Another way for Venus to be closest, I'll just throw in the angle 1.5, 0.5, 0.5, all radians for those 3 planets. And then in this region, so we got -5, so Venus is the closest. Okay, so in these two regions, Venus is the closest. This separates who's closer between Mars and Mercury. I think Mercury is closer above and Mars is closer below. It's about a process of elimination. These two regions, Mars is closest, but take a look. With these angles, I get 13. That means Mars is the closest. So in that region, Mars is the closest. And in this region, I get 11, which means Mars is closest. So in these two regions, Mars is closest. Whether between Mercury and Venus, who's closer, that would be determined by crossing that surface, but I don't care about that. So now, if all angles are uniformly distributed, 0 pi, 0 pi, 0 pi, so I've got this solid 0 to pi cubed, so this has volume of pi cubed. I'm going to find the volume of each of those regions where a certain planet is the closest. For Mercury to be the closest, we're in these two regions, so I want to integrate above this surface up to pi, from this curve to pi, as Mercury's angle, which is S, goes 0 to pi, right? So for Mercury's angle going 0 to pi, I'm going to integrate above this surface. That's all that matters. This, can't highlight it, but I'm pointing to it. This surface right here, above that surface. But I don't want that part. I only want the y's, which is that way, from this curve on up to pi. And that's what I have here. So we integrate from the one surface to pi in z, from the other curve to pi in y, 0 to pi in x, divide by pi cubed. And Mercury will be the closest of the three planets now. So if you measure how far Mercury, Venus, and Mars are every day, for 10 million years, then 46.5% of the time Mercury would be the closest. Mars was in these two regions. Right, so for these two regions, I still need to be below this curve though. So I'm going to integrate from this curve right there kind of to pi. That's sort of in my y direction, but only for those z's that stay below this curve. So I should say this surface. So from this surface to pi for y, only for those z's that are below this curve. And Mercury, or x, can go 0 to pi. So I have that here. Hope you're able to follow that. So that one surface to pi in y below the curve in z for x going 0 to pi. Okay, because I have to stay below this curve. So this surface, all right, that all makes sense. Now for Venus, it's in these two regions, so there's a couple ways to do it. I did it by integrating first y from 0 to this curve, or I'm sorry, 0 to this surface right there, below this curve, kind of the complement of the Mars part. But let's redo it. So from 0 to this surface in y, below this curve in z, 0 to pi in x. And then I'll integrate, I'll just do it with z's going from this surface up to pi. Right? So this surface on up to pi for those y's from 0 to this curve right here of this intersection. Well, this curve right here is where it intersects. So for y's going from 0 to that curve, and x goes 0 to pi. Okay, so above this surface but only until you reach this surface, this curve, for all x is going to 0 to pi. So that's a sum. So that was this region, I did y first, 0 to this surface, z's under there. So it was the sum of the two integrals. So Mars gave me like almost 17%, Venus almost 37%. If I add them up, lo and behold, I get 1. So that's the result. So we can kind of visualize who's closest that way and do it analytically. I did Venus, if we're on Mercury, then the average distance Venus is to Mercury is about 0.78 astronomical units. I did it two different ways, of course. The average distance Earth is about 1.03. Well, we already did that the other way, so it's symmetric. So Earth's 1.03, 1.04 astronomical units away from Mercury. So Venus, of course, is closer. There's the other way. The average distance Mars is, don't really need, but it's 1.54. Now, Mars can never be the closest planet to Mercury. So Venus at its farthest will be Mercury plus Venus's orbit away. Mercury plus Venus's orbit is less than Mars at its closest would be Mars minus Mercury. So if you do Mars minus Mercury, that's more than Venus plus Mercury. Right, get the distances here. But we can still compare Earth and Venus. So here's a plot. Right, so T is Earth's angle, S is Venus's angle. There's where they're equal. First I did it this way. There's the top half and bottom half of the negative arc cosine. Vertical asymptote there. But so chi right there. For these angles, Venus will be closer. Right, so no matter what Earth's angle is, Venus is closer until it reaches this angle. And then after that, which I have labeled right here, is about 1.01 radians. After that, Earth can be closer. So Venus has to have kind of a big angle. So Earth is closer in this area. Venus is closer in this area. If I take the ratio, you see, if I integrate from the 1.01 to pi, about 26% of the time, almost, Earth is closer than Venus to Mercury. Recalculate it this way, so that's how you get this value. I did it another way as well. So about 74.3% of the time, Venus is closer to Mercury than Earth is closer than Earth is. I'll leave it as an exercise to the viewer to fix Venus and then do what percent of the time Mercury, Earth, and Mars. So you'd have to go back to that 3D stuff. All right, so there's the analysis. It matched pretty well with the results here and with the email. So I feel confident in the results. All right, so that is the results. Hope that you're able to follow that. I know it wasn't easy, but thanks for trying and have a good day.